Hello everyone and welcome back. So what I want to do now is get into some very practical results on how to prove that Fourier series converges to its function. So the first thing we're going to look at is called Dini's theorem, and we're going to look at what's called the Dini condition. Sometimes this is called the Dini-Dirichlet condition. Okay, so remember the partial Fourier sum corresponding to f is just k equals minus n to n, f hat of k e to 2 pi I to x. And I believe it was 2 videos ago, we had a formula for f of x minus snf of x, which was true if f was L1 on 0 to 1 and 1 periodic almost everywhere. Okay. So and that formula was this here. Okay. So what I want to do now, before I just dive into the statement of a general convergence theorem and its proof, I want to explain intuitively why it's even reasonable that as n goes to infinity, this quantity here is going to go to 0. Really, right off the bat, there's no good reason to think that a function should converge in any way, shape, or form to its Fourier series. I mean, like I said, back in the 1700s, Fourier made this assertion that all nice functions can be written as a Fourier series, and if I have my history correctly, particularly Lagrange, the famous Lagrange, wasn't too happy with that statement, somewhat rightfully, because there's absolutely no justification for it. Real justification didn't come until the 1800s by Riemann, Jordan. We'll look at Jordan's theorem in the next video. Dirichlet, Dini. Okay, so right, so let's explain what's going on here and why this should be true for nice f, and then particularly what should we look for to prove a convergence theorem? What conditions on f should we look for? So fix x, and let's say gx of f is this function that I'm circling right here, right? Okay. So that f of x minus s and f of x is 0 to 1, gx of t sine pi 2n plus 1 t, that integral, all right? So, right, so let's look at sine pi 2n plus 1 t. So it's going to, fairly rapidly oscillate from 1 to minus 1 and so on and so forth. So in particular, you can see that from 0 to 2 over 2n plus 1, it makes 1 full period. From 2 over 2n plus 1 to 4 over 2n plus 1, it makes another full period. I mean, plug in 2 over 2n plus 1 into here, and you literally get sine 2 pi. So what's inside here, what I'm circling on this interval from 0 to 2 over 2n plus 1, what's inside that the circle goes from 0 to 2 pi, etc. All right. So that's a very, very important observation, that we have many, many, many full 2 pi periods of sine, for sine here between t for t between 0 and 1. And as n goes further and further and further out to infinity, the amount of time it takes, or rather the interval for each 2 pi period of this whole thing here, gets smaller and smaller and smaller. All right, so let's use that observation, intuitively at least. And if we take, let's say tk is 2k over 2n plus 1. Let's write, not terribly subtly, 0 to 1 as a disjoint union of these intervals. The sine function here that I had before completes a 2 pi period on each of these intervals. Okay. And if we do this, we're left off with the last one, 2n over 2n plus 1 to 1. And sine completes half of its 2 pi period on this interval here. All right. And just for shorthand, because this is kind of a pain in the ass to write all the time, so we're going to write this as tk plus 1, where tk is what I just had a moment ago. All right, so let's assume gx is continuous. And when you think about it, it's not a wild assumption. If gx is L1, then in the L1 norm, we can approximate gx by a continuous function. And that's actually the heart of what we're going to do rigorously in a moment. Okay? But for the time being, let's just intuitively assume gx is continuous. So on this very small interval, which has width 2 over 2n plus 1, gx of t is roughly gx of tk. Right. And on this last interval, gx is roughly gx of tn. Again, this interval is tiny. Its width is, well, it's also, sorry, this width is 1 over 2n plus 1, so it's even smaller. Okay, so let's break up 0 to 1 according to this disjoint partition. All right. So I'm just using the triangle inequality for this finite sum. I'm not smashing in absolute values anywhere. That would be a disaster if I smashed in absolute values. Because when you have the sign here, as we'll see, we're going to need the fact that, we have positive area, for each one, sorry, for each 2 pi period, we have, we have both positive area, takes a little bit of time to fill that in, but we have both positive area and negative area, all right? Okay, and we have, last but not least, this integral here from this partition here. So again, we're just doing everything intuitive. I'm not proving anything. I'm explaining why this should be true for nice f and what conditions should we look at on f to possibly make this rigorous. I already hinted at one condition, which is gx is integrable, because then we can approximate gx by a continuous function in the L1 norm. And that actually turned out to be the key assumption, as we'll see in a little bit. All right, so like I said, gx is roughly gx tk if it's continuous. So let's just intuitively pull that out and pull out intuitively the gx tn. And right, as I mentioned, on each of these little tiny intervals, sine makes it a complete 2 pi period. Or just do fundamental theorem of calculus. You can just see that each one of these integrals is 0, which I've done explicitly for each of these here. But the trivial fundamental theorem computation works for this last integral also. Again, besides just plugging and chugging into the fundamental theorem, what really, as I mentioned a second ago, is going on is this extremely important concept of cancellation, which will be omnipresent for a lot of this course. And is that, here the idea is that we have, in a full 2 pi period, we have positive area canceling with negative area for sine to give us 0. Okay? If I smashed in absolute values, what would I have here? Well, I would just have this. Well, kind of hard to draw here, so try to do a little better. It's a lot better. If I smashed in absolute values, I would be in big trouble because I would have literally all these, absolute value of the sine function. And none of these integrals that I wrote down, if I have absolute value here, none of these integrals would be 0. They're not 0. None of these integrals would be 0. So, so the key idea here is the cancellation from sine, the positive area canceling the negative area. Okay, and this rough philosophy really underlies, the Riemann-Lebesgue lemma also. And you can actually make a very careful proof of the Riemann-Lebesgue lemma using this philosophy here. I'll very briefly outline it. I still think integration by parts and the approximation by C1 functions is much quicker. But if you do want to prove the Riemann-Lebesgue using this rough idea, feel free to do it. Right, so what's Riemann-Lebesgue? So Riemann-Lebesgue, remember, is we're looking at the Fourier coefficient, and I forgot a minus here. So I have to stick the minus here. Not that it matters, really, but it should be a minus. Yeah, so remember, Riemann-Lebesgue is that if f is an L1, we want to look at f hat, the Fourier coefficient of f with k plugged in, or sorry, here I have n, so I want to look at n plugged in. And that's going to be this integral here. All right, so just f might be complex valued, so just break this exponential up into sine and cosine and use triangle inequality, nothing very deep. Again, we don't want to smash in absolute values inside the integrals. Whoops, sorry about that. So here we go. So I'll just look at the sine bit. You can play around with the cosine bit if you want, same idea. So here we're going to do basically the same idea. Break 0 to 1 up into these tiny little intervals where what's inside here, the sine bit makes a full 2 pi period on each of these intervals. And here we just, these intervals are just k over n to k plus 1 over n. Plug in k over n here, you get 2 pi k. Plug in k plus 1 over n, you get 2 pi parentheses k plus 1. Okay? So it's a full 2 pi period. Okay. So we can assume f is continuous. Again, this is, I'm giving an idea of why Riemann-Lebesgue is true. You can make this completely rigorous by approximating an L1 function by a continuous function on 0 to 1. So intuitively, we can assume f is continuous. Hence, it's uniformly continuous on 0 to 1. So you can make it fairly rigorous, quote unquote, popping out f of t and replacing it with f k over n. Because on his interval, f is roughly, if it's continuous, f is roughly f of k over n on this tiny interval of length 1 over n. And the same thing here, on each of these intervals, sine makes a complete 2 pi period. So this integral here, there's a lot of cancellation going on. We get 0. And again, the picture is just shown here. Yeah, the idea of this positive area here canceling the negative area here. right? Or, I mean, you can also think with f of t being roughly f of k over n, you kind of get, you know, almost the, yeah, let's just leave it at that. I think it's better to think in terms of popping out the f of k over n, and then you're left with this integral here, which is going to be 0. Okay? Again, using uniform continuity of a continuous function, you can actually make this completely rigorous. And you can use this argument, f is an L1 approximated by a continuous function, the L1 norm on 0 to 1. You can make this argument absolutely rigorous. Like I said, I still think the integration by parts proof is a little easier, I guess, but anyway. Okay, so what's Dini's criterion? Well, I basically alluded to what it is. So let's say we have f is an L1 and it's periodic. So we take an L1 function again on 0 to 1. It's pointwise defined almost everywhere. And just almost everywhere, we periodically extend it on each interval 1 to 2, 2 to 3, -1 to 0, -2 to -1, et cetera, et cetera. We don't really care how we define it almost everywhere on all these intervals. So it's one periodic modulo set of measure 0. All right, so, and let's say f is defined at, pointwise defined at 0 to 1. So by that, I mean it is an actual number. It's not plus or minus infinity. Okay, so let's suppose there exists a delta where this function here for fixed x has finite integral. And in practice, I should say, this is a very, very easy to check assumption. And we'll do examples on when this is, when this is true. If this is true, then we have the Fourier series of f at x converges pointwise to f of x. Okay. All right, and what's really interesting about this proof is that the outline I gave essentially is the proof, in the sense that this condition here is exactly what is needed to invoke the Riemann-Lebesgue lemma. And the proof of, I just said, an outline of the proof of Riemann-Lebesgue, one of many different proofs, is that, it's fairly easy to prove via this cancellation of sign for continuous functions, and you approximate a continuous function in L1 by, or sorry, you approximate an L1 function by a continuous function. Okay, and right, roughly speaking, this condition is exactly more or less what is needed to apply the Riemann-Lebesgue lemma. Or in other words, to apply this idea to this function here. And that's not surprising, because particularly around t equals 0, we know that sine, should know, is basically, well, roughly pi t. And the limit sine pi t over t is pi. Okay? So this basically here behaves when t is small like f of x plus t minus f of x over t. We do have a problem when t equals 1, but we'll handle that in a second. That's easily handled by the one periodicity that we're assuming for f. Right. And actually, the fact that we're also not just going from 0 to delta minus delta to delta, that actually handles the problem at t equals 1, as we'll see in a moment. Okay, so the proof is we're going to just take this integral here. We're going to break it up into basically three integrals. Using a triangle inequality, just not smashing absolute values inside, but just breaking this integral up into these three integrals, and in that sum, that finite sum of really just the sum of two pieces, this one here and this one here, we use the triangle inequality. Okay, now let's call this A and B, and we're going to apply Riemann-Lebesgue to A and B. And we're going to recognize in each instance, what I have here is essentially, it's essentially the Fourier coefficients of a certain function. Not exactly, but essentially. Okay, so let's say g of x is exactly what we had before. G of x, remember, is this one right here. F of x plus t minus f of x over sine pi t. Okay. So, right, let's look at these two together. And this notation should be fairly obvious. It means I'm taking the integrand here and integrating 0 delta, and then plus taking the integrand here, integrating delta to 1. All right. So what we're going to do is write sine in terms of complex exponentials. Nothing subtle there. It's either I pi 2n plus 1 minus e to the minus I pi 2n plus 1, t with a t there, over 2i. All right, so this is going to be equal to the following, okay, which you should recognize as a whole bunch of Fourier coefficients. I mean, usually, Fourier coefficients go from 0 to 1, but that's all right because we're just throwing in cutoff functions. If we're going from 0 to delta, delta to 1, right? And when we have a minus here, so actually I have it flipped around. This one is the positive Fourier coefficients, and this one are the negative Fourier coefficients. So I probably should put, I should probably flip these around, but whatever. All right. Yeah, and by the Riemann-Lebesgue lemma, this is going to go, all four of these are going to go to 0 as n goes to infinity. If we can check that both of these functions here that I'm circling are L1, let's do that. You absolutely need an L1 function for Riemann-Lebesgue. All right, so yeah, let's check that. So we have to check that this here is finite. Well, we basically, there's really nothing to this. As I mentioned, for delta small, sine pi t behaves like pi t. So just multiply and divide by t. Strictly speaking, this quantity here is increasing on 0 delta for small delta. There's a removable singularity at t equals 0. It's the limit is 1 over pi. But anyway, so the Dini condition is that the integral from minus delta to delta, this here is finite. So certainly this is finite, right? And here we're assuming delta is smaller than 1. Right. Okay, and this one here is basically the same thing. So the only thing is we're going to use the fact that f is 1 periodic almost everywhere. So we're going to do a u substitution and just do u is t minus 1. So that makes this going from delta to 0, we use one periodicity of this function here as a function of t and sine pi t. And this is also finite, which, as I mentioned, really handling around 1 is the other half of the Dini condition, minus delta is 0. Okay, right, and so B, this other term here, is basically the same thing. It's Riemann-Lebesgue. It's the exact same integrand. It's just we have a different interval here that we have to check gives us an L1 function. Right, so let's do that. And this one's actually really, we're just assuming f is defined at x, so it's a number, not infinity, and f is L1 on 0 to 1 and periodic, one periodic almost everywhere. So particularly, just throw out the sign. By periodicity or rather symmetry, sine pi t, 1 over sine pi t for t near delta is the same, and absolute value is sine 1 over sine pi 1 minus delta. Or, sorry, 1 over sine pi t for t near 1 minus delta. Okay. So delta could really be really small, and hence this could be really big. We don't care. Delta, I want to emphasize, if it's not clear, is just some tiny positive number that's fixed. Okay? Delta is fixed. So no matter how small delta is, it's fixed. This is something not infinity. Okay. And henceforth, here just smash an absolute value. Like I said, just do a use substitution for this one. Here it is integrating f of x from 0 to 1 with respect to dt. So just there's nothing really. It's just multiplied by 1 over sine pi delta. That's finite. I didn't actually write it, but this is finite. And again, if it wasn't clear here, well, here actually it doesn't really matter delta. I mean, this here is, we can handle delta being really tiny, but anyway, still delta, well, so as I mentioned, this is increasing on 0 to delta for delta small, but anyway, so. All right, yeah, that proves it by 2 applications, like I said, of Riemann-Lebesgue. We've carefully checked that, what we're applying Riemann-Lebesgue to is all L1. Okay.